Welcome everyone. Today we have our another new episode, and we have our world famous speakers. We will discuss on 3D imagings, and uh, we have our speaker, Mr. Marshall, Professor David Smith, Professor Donalds, and we have our new speaker, Mr. Cho. I think he is from Tando. He is one of the fellow from Tando. So thank you for joining today's session. First, I would like to give chance, Mr. Marshall.
Well, thank you, Sharif. This is a great topic, imaging and graphic imaging, which, as David and I know, and I'm sure Donald knows, and it's a good pleasure to meet you, Mr. Cho. But the topic is broad and vast today. I was involved in imaging and graphic imaging back in the 70s and 80s when I was on the board of the the Association of Graphic Communications in New York, which is part of the Printers Association in the United States and internationally. So the American Graphic Association was involved in a lot of bringing 3D to the table. It's evolved over time tremendously because of technology. In the beginning, graphic imaging that was really advanced back in the 80s and 90s was a form of stochastic imaging, which is a random dot pattern that was developed. And I was involved with that with a company out of Europe called AGFA. And AGFA in New Jersey, their corporate headquarters there, we were involved in bringing stochastic processing to the imaging space, originally for printing, and then it became digital over time. So that's my intro to the part. I'll let others explain to it. I'm sure David will know what the value of the market is in the various domains. There's probably, I don't know, maybe 20, 30 markets alone that just fit this category, and they're all different. And I'll let the next speaker go.
Thank you, Mr. Marshall. Professor David Smith. Yes, we are interested to learn more about this topic. I know you have many things to share with our audience.
Well, thank you so much. I guess I do have to throw the market numbers out now after Marshall. If you just look in the United States, though, the market forecast for 3D imaging, actually it was almost $16 billion in 2021 and is expected to grow to $44 billion by 2027. So that's not a tremendously high compound annual growth rate. It's only about 6.5%, but as such, it really is growing and beginning to do things. What really is, when you look at 3D graphical imaging, and as it begins to be used in many different types of multimedia applications, you see that it's a display mechanism providing detailed, really spatial characteristics about a particular object. On the other hand, this 3D imaging is really across many, many different areas, such as in consumer electronics, with notebooks, laptops, smartphones, and healthcare, where part of this really got its very early software start in areas like ultrasound, MRI, CT scans, and others. In industrial applications, particularly in manufacturing, industrial automation, and really entertainment's where it's beginning to go in now, with the re-emphasis of some of the 3D televisions that had a false start earlier and then are beginning to come back, video games and others. So you see the really come back in there. One of the key drivers, though, for 3D is there is a demand for higher and higher resolution in what we do, and beginning to see the other elements, particularly in the medical imaging, particularly in the defense and intelligence industry. You're seeing it. Also, as we're seeing more and more, not just robotics automation, but really autonomous automation in manufacturing, and even in the use in the cars, you're seeing it really begun expanding even more. And there's an increased emphasis in machine vision applications for this type of 3D opportunities. The biggest challenge today is you begin to see this is interoperability across all the domains. Entertainment, you're seeing it in manufacturing, and in healthcare, is that there's a lot of applications beginning to use this type of 3D imaging, but they haven't set up a standard yet. They're not interoperable. And you begin to see this coming. That's really part of the next generation you'll see is attempts at global standardization. I know ISO has several groups right now which are working on 3D imaging, trying to set a new bar for interoperability and how it can be used. So Sharif, I hope that answers it. And Donald, I'm glad I could give you some market numbers.
Mm-hmm. Thank you. Thank you. Professor Donald, what you want to add to these discussions? I think after you.
Well, I want to bring out something that actually adds to what David just said. I'm going to just take one fascinating case. If you've ever listened to the show before, you'll know that I'm extremely skeptical about the ability of artificial intelligence to do a lot of the things that people claim that it'll do. And one of the things that I have been skeptical that it'll do is to allow self-driving cars. And I found out that, but yet self-driving car, there's a company called Mobileye, which is being quite successful with self-driving cars. And they're not using artificial intelligence. What they've done is they've done basically a system with all of the what's the name? Where basically all of their cars have cameras on them. So basically, what happens is the problem is if you had a perfect map of everything, the car wouldn't really have to have any intelligence because it would just you could simply program in if this, then do this. If this, do this, because it would know where things were. And then it would have to have some intelligence because it would a very simple intelligence saying, well, if something's different than what you expect it to be, then do this. Okay, so it wouldn't have to make guesses about what things were. It wouldn't have to guess what's around the next corner. It wouldn't have to do all the things we do when we're driving and have real intelligence. But the problem with that is if you created a map, the map is constantly changing because cities are constantly changing. Well, what they've done is they put basically a system like Waze, where they put cameras on all of the cars. Their cameras all work together to build one 3D map that everybody has access to. So all of the cars, so that they have a 3D map that's continually updated by all of the cars, so that at any time they have an almost real-time map of what's going on in their city. So the way that they get it to work is with basically 3D imaging. And so I think that's really, really cool because they got past the issue that artificial intelligence is, or what they call artificial intelligence, is actually extremely limited. It can recognize objects, but it can't make any guesses. It can't make hypotheses and try and it basically can't. It doesn't understand that something's a problem. It can just basically recognize patterns and then do what you tell it to do from the pattern that it recognized. So, but that's not a problem if you know. I mean, that you can get it to work if it knows. If you have a map of everything. And so by using 3D imaging now, they've been able to create maps. I don't know if it would work in rural areas so much, but it works great in cities like New York and Munich and places like that. So that's a really exciting example of how 3D imaging is being used.
Thank you. Thank you. We have our subject matter expert, Professor Cho. I think he has innovations and he has his own company. So we will get more interesting informations from Professor Cho.
Okay, so in 1980s, before I came to United States, my specialty was robotics. That it was very primitive 3D technology. So at the time, we tried to convert 3D image of the face into the actual 3D using the robot. And in early 1990s, I came to UT Austin to get my PhD degree, and I was so lucky, and I had experiences at the a very early stage of the 3D printing technology using it was called selective laser sintering. MIT, Stanford, and UT Austin was leading the 3D printing technology at the time, and I was involved in the project that connects 3D printing technology with AI. It was a very primitive AI. It was analogical reasoning. And so I had the good chance of working with the 3D technology. But my starting point was the 3D printing and the AI instead of the 3D imaging. So 3D imaging was very relatively new to me. After I got my PhD degree, I was working for the 3D, the optical drive company as a engineering director, and I learned about the hardware that is required, that is necessary to get the 3D images with precision. With that background, I could raise a funding for the 3D motion technology. At the time, there was no the Kinect from the Microsoft. It was even before the Microsoft Kinect was developed, and our company was using a Zcam from the Israeli company. There was very few number of the 3D cameras, and we used that to control the game using the body gesture. We were using the soft Kinect. So it seems like that there's two different paths of the 3D imaging. One was for focusing on the accuracy of the critical points like the skeletons, and the other one is how to use uh, very huge number of the cloud points using the different types of the 3D scanning technologies. Right now, I'm working the Dallas College had a $3 million grant that for the 3D education. In Dallas College, as a professor, I was involved in how to use the 3D technology for the future. So I was very interested in learning about how to educate 3D technology for the future students, and also I was very interested in how the 3D technology will be evolved in the coming decades. So right now I'm working on the NSF grant for the Bridges 3D technologies because I feel that 3D printing technology, 3D imaging, 3D programming, just such as WebGL, and also some of you already mentioned about AI. There's huge room to make a very strong synergy effect by integrating those technologies. It seems like that those technologies and theories or areas are separated, but actually it's very well integrated together, and there are very huge room to connect it together. So, for example, one of the project I'm working on is to using AI and the very primitive 3D pose 3D skeleton detection algorithms. I'm developing by using the dynamic motion of the people. What if we can estimate the skeleton of the spine shape of the people? I think it'll be a very interesting example about that integrates motion detection, AI, and the 3D programming all together.
Thank you, Professor. Thank you, Professor Cho. Mr.
You.
Adam, what you want to add for today's discussion?
One of my main concerns regarding this subject is the deepfake. We have already crossed the threshold where many human observers can be tricked into thinking that a well done enough deepfake is the real deal. The ethical and moral implications are dramatic. I fear that in the near future, this technology will be used to frame people for political and criminal and coercive purposes, blackmail and such. I mean, we could say that all deepfake creating and animating software should have something embedded, like some kind of watermark to make deepfakes distinguishable upon examination. But of course, the problem with that is no matter what rules or laws or regulations are enforced on surface level society, at least, there's guaranteed black market counterparts that work around and find shortcuts around laws, which also happens in intelligence and black ops as well as criminal enterprises, of course. I do have quite a lot of faith in people's observational skills where something feels off or not quite right, which is, of course, where we get the uncanny valley effect from others. So, of course, deep fakes and contrived simulations of real things have these obvious moral implications. But I also worry that the more widespread deepfake art and creativity and espionage becomes, where it may even become easier and easier to make convincing simulations for less expensive software and equipment each time, like music production, for example, it could cause a negative psychological impact in people where the connection to reality starts to become more and more tenuous and people's confidence in their own ability to distinguish reality from fantasy starts to wane, leading to mental health collapse. So those are my thoughts for now.
Thank you. Professor Ching, what you want to add for today's dialogue?
Yeah, okay. Thanks for waking me up during this. Anyway, let's say something about the topic, you see. And then I will go to my own stuff in post science. So, Dr. Kuni, as I said, Dr. Kuni was my best friend in Japan. He and his wife are the top computer scientists in Japan. And his field is computer graphics. Okay, he started the Computer Graphics Society in Geneva, Switzerland. So he his work. Okay, let me describe something about his work. His basic theory is a homotopy theory. Okay, homotopy theory deal with Moore's law, graphics theory, and differential graphics theory. It's very mathematical. Okay, he's for vector graphics. He's against triangulation. And today, both vector graphics and triangulation are taken over by bitmapping, NVIDIA. Okay, so they think vector graphics is out, but I think there's not enough smart people to really get into this. Okay, what it really amounts to is this. Okay, I studied for some reason I went to took a course from Professor Moon. He teaches a field theory for engineers. Okay, the field theory talk about coordinates. Okay, anything we see a round object, we use the polar coordinate system. Normally we use the X, Y, Z. This straightforward. Then there's a polar coordinate, all kind of coordinate system. So what you do is you use Jacobians to transform from coordinate to coordinates. And according to Cooney, he comes to Silicon Valley quite a lot. But the people he used are from Russia. Okay. The cold weather probably is good for sitting down, do very deep mathematics. Okay, so now Cooney is gone, so Russians stuck in northern Japan, working on his graphic theory. But I still feel this Cooney, to me, is still the most advanced system. Another thing I should mention regarding the most advanced state of this thing is, I mentioned triangulation and PostScript, 3D graphics. Okay, the PostScript, we are familiar with the Adobe PostScript for characters. Okay, what they do is they use lines, and angles, to describe a character, which is very simple. In other words, use one dimensional to describe two-dimensional thing. But for three-dimensional graphic, they probably need to possibly go back to triangulation. Okay. Use a surface, 2 dimension to describe 3 dimension. So that's pretty much the state of art of what's going on with graphic theory. Obviously, for 3D, they got to take many pictures and they put it together and it becomes 3D graphics. Okay, what I need to say something about my own thinking about all this. Okay, first thing I would say is that, the human technology today is just not very advanced, in my opinion. So, for example, Pole Science is working on complete automated software. Okay, from the complete automated software, we can see the living system is the most advanced technology today on Earth. Okay, human technology is way, way behind. Okay, when I work with Sadeh, his work on fuzzy logic is, I would say even ahead of all my work in pole science. So he's about 4,000 years ahead of everybody. Nobody can understand what he's doing. And I have to explain what he's doing in order for the world to continue on fuzzy logic on its own terms, not on the term of engineers. Okay. So the living system, what living system has done is this. Okay, human being separate hardware, software. Okay, we have hardware, we have software. When we design a chip, we have 2 languages. We have a structural language, we have discrete language. For example, in Verilog. Okay. There's another thing which is missing. Okay. You have hardware, software. Can you use today's hardware, software to create a robot part or create even a 3D-dimensional graphics? Okay, so now let me describe a little bit about this very advanced thinking. Okay, even though we are totally dissociated with this establishment. See, that's why I purposely avoid the talk on the best innovation, the most important innovations, because we disagree with everything. Okay, the most advanced is just totally worse than our worst. Our worst is valuation, which should be used to judge the advanced innovation. Okay. All the advanced, you don't have a method of evaluation. How do you know which is the most important? You see, and also our valuation system has saved the world from financial crisis. Okay, it's the only system which can continue to save the world from financial crisis. So basically, this is most important thing, but to pole science, it's the least important. Everything else is more complex, hard to figure out. So the living system has hardware, software combined into a DNA protein system, plus graphics. Okay. So nature has managed to combine all 3 into one. Okay, human being has all separate, has cannot visualize any possibility for graphics to join this hardware software. They just concentrate hardware software. How does this graphic join into the human, into the living system? You see, it basically through this simple concept of embryonic folding. Okay, in other words, you have a trilaminar disc undergo embryonic folding. Okay. Initially start with fertilization, implementation, then gastrulation, then you neurulation. So you form a cell, and this cell will fold. When it folds, one end will become the spinal cord, the other end will become the head. And it fold and they create a graphic, and they create a human. Okay. It's not only in 3D graphics, it's actually in 3D object, 3D printing. Okay. Another way, it does 3D printing correctly. Okay. Today's 3D printing, you just print layer by layer. That is too simple. Okay. You know, again, you need to go back to Russia to get all these mathematicians to work on this project in order to have it get anywhere. Okay. Today, the world is completely money oriented. Like Adam says, you know, there's people because of money they do anything. You know, so you know, and nobody is going into knowledge. If you go into knowledge, then you will be poor because you don't have time to make money. So you know, we're stuck. Graphic series is a very difficult series. It's very difficult. It's really creativity, mathematics, manipulation. You know, thinking about how mathematical manipulation. It has to be the best mathematician to get into this. So basically, that's my comment.
Mr. Marshall, what industrial things you want to add for today's discussion?
Well, I think Hugh brought up some very good topics, and 3D printing is obviously where this area has advanced since I was involved in it back in the 70s and 80s, and a lot of the basic concepts have migrated. And I also want to sort of address what Adam has brought up, some of the concerns of how technology can be used for ill-gotten gain or for harming others. I think it's an important topic as well. And if you look at those two topics, they're combined. They can create opportunities that we're seeing already in warfare in the Russian-Ukraine war that's going on. And we're also seeing it in cyber warfare as well. People putting out images that look real when they're not. And the three-dimensional aspect of it is important as well. From a positive point of view, I would say that what we're seeing actually implemented today, and I'm involved in this as those who know me on past programs, we're mostly involved, though I have a wide range of experience in the graphic arts and marketing, but most of our business is now formulated in carbon sequestration, climate repair, and climate restoration. And with that regard, 3D imaging is really important when you're processing waste and converting it into something that is positive as opposed to a harmful material. So that the reason that's important is because some of the materials and wastes that we're dealing with are toxic, and you don't want to have any human next to it or near it. So getting 3D imaging is really important because you can see objects in the waste stream that you normally might not pick up, and we're experimenting with that as well. So I would say that obviously, like anything else, imaging, both 3D and 2D or 4D, whatever you want to call it, it's got its pluses and minuses. Our focus is obviously using it to the benefit of humans and humanity and the environment. So that's my take for right now.
Thank you. Professor David Smith. Can you unmute, please?
Yeah, I really enjoyed this discussion so far. One of the places where I spent a lot of time understanding 3D was in the work I did with the National Imaging and Mapping Agency and the National Geospatial Intelligence Agency in the United States. And NGA, the National Geospatial, is in charge of putting together mapping, satellite images, other imaging from aircraft and other devices, and building actually 3D environments of it. 3D digital environments, in some cases, actually taking the 3D digital environment and building 3D models and other things for it. For a place where that was used was, for example, the mission that went to capture Osama bin Laden, where this type of 3D imaging was used to actually build a very good replica of the compound where it's being used. You see it used, for example, in planning. NASA uses 3D imaging to begin to plan intricate missions they want to do, for example, outside of the International Space Station, or what they want to do on other planets with some of the robotics and some of the drone technology they're trying to use there. So it really is a technology that is being used more and more widely today as you're seeing things put in place. There also, though, is a lot of opportunity in the research community today to take what it is and extend it, particularly in computer vision and in robotics, where they began to extract 3D data for, I guess, over 3 decades now. But it really must take into the fact that there's still imperfectionist of depth information. And there's still challenges when you try to move this beyond 3Ds into 4D, 5D, and 6D, which are necessary for some of the things where this can be applicable. I see, though, that the ability to begin to look down into 3D more and more at lower and lower costs are really beginning to create opportunities for entrepreneurship, for the ability to begin to look at products in new ways that are going to leapfrog over older legacy products that do not have the ability to look at 3D. And you're now seeing 3D cameras built into even smartphones and others like that, which are going to have a big opportunity there. The other thing is there are now multiple conferences coming out, which begins to focus on 3D. IEEE, for example, has several conferences coming out where 3D is part of what's going on with it. You see, like I said, ISO has standardization efforts there. You go into the semiconductor industry where 3D chips are becoming a reality so that we can stay close to Moore's law. And this type of 3D imaging is now beginning to have to move to have scanning electronic microscopes begin to accomplish 3D imaging as you look at how you tunnel the 3D through the microelectronics chip and how it can be used. And as we begin, as we've talked before, with new forms of computing, particularly biological computing, the ability to do 3D imaging is going to be a driver. As we look at biological computing, biological storage, as it moves to a new level. And this is going to be one of the key technologies that will enable more rapid advances in that area. But it's one where I'm fascinated by the development and by the opportunities we see. And because the advanced 3D imaging, particularly when you add time and other dimensions to it, it's a great opportunity for global development because the technologies are becoming, like I said, cheaper. You're beginning to see them incorporated in consumer devices, and that creates an opportunity for really a very robust startup community built around this, independent of geographical locations. So it's one that I believe you'll see a lot of work coming together in the next 5 to 10 years as this matures and the prices continue to fall. So, Sharif, thank you.
Thank you, sir. Professor Cho, you are from research industries and World Talent Economy Forum. We are actually inspiring developing nations. to engage with more research. So if you share more of your experience from the research industries, how the youth can get more opportunity to engage with this kind of research and innovations, maybe it can inspire more the youth community from developing world, from Asia Pacific.
So it was more than the research. I was focused on the integration of the technologies. So you can call it the research, but I think it's a little bit different view. And the when I, as a reviewer of the IEEE multimedia transaction, I could see lots of effort to try to integrate 3D imaging with AI. I think it's a very natural trend because there's people are developing a 3D hardware and developing the software, but they start to realize the limitations of that and the benefits of integrating it. So, for example, there are different types of the 3D scanners, and each has the pros and cons. They try to make a fuse the 3D scanning technologies, but there's still a gap in between the ideal 3D imaging we can get and the actual 3D imaging we can achieve. So I think that the human nature has eye. It's a really good hardware, but without brain we cannot make a 3D imaging perceptions. So I think it'll be a very good research area, and also from the industrial standpoint of view, the mass customization is one of the key topic that involve the 3D technology. So it's a very primitive, it's a very simple example, but if you can have a graduation statue that can be automatically produced, it requires a 3D scanning images and 3D printing technology, the integrate together. So I think and also you may have seen lots of the mass customized 3D scanning products, such as artificial leg for the patients who lost that. So medical industry has already started to use mass customization of the 3D scanning and the printing technologies, and I think it may spread out to the whole the industry instead of just the medical industry. So I think that may be interesting research topics to move forward.
Thank you, sir. Professor Ching, yeah.
Yeah, okay. Well, I want to advertise something I have been asking Sharif all the time. You see, this is 3D graphic will be used in double hitting by robots. Okay, I asked him to double hit. I asked all my students to double hit. And the human can double hit a ball in one smooth stroke. The robot cannot. Okay, robot need real good senses. You need the eye, even need the brain. Okay, so this is called Ching test, testing robot ability to double hit. When robot can double hit, they will take over all human physical labors. So this is double hitting demonstration is not a trivial demonstration. It shows the humans are different from robots. Okay. It's such an important, demonstration. It's much more important than tuning test, all this kind of tests of common sense of machines. We are testing something real. Okay. Today, everybody try to build robots, build driverless cars. Do this double hitting. Okay. Then you understand there's something they're missing. Okay. Cars, avoiding cars. But when cars collide with cars, that is double hitting. That's a touch. Okay. It causes people to die. Okay. It's very important. We need to study collision rather than collision avoidance. Okay. So all these priority are not going in the right direction because nobody knows how to make decisions. Okay. There's no solution value. Nobody can make decisions. So basically, I would say that One time Dr. Cooney was giving a talk at UC Berkeley and attended by Professor Ramusi, Lofty Sadeh, and myself. It's a historical lecture. The Lofty Sadeh, is the leading intellectual of the world, and he's listening. And I asked him a simple question. I said, "You're a tree." He draw a tree on the blackboard. I said, "The tree. Did you create this tree from one cell or from multi-cell?" Okay. What I meant was living system grow from one cell into a human. Okay. This question pretty much summarizes what I would like to say on graphic theory. Also, Cheryl woke me up, so I'm so my soul is still sleeping. In any case, doesn't matter if you can hear me, that's good enough. In any case, there's mitosis and meiosis. Okay, mitosis has been demonstrated by pole science. Okay, I create this self-generating, complete automated and self-generating software system. One of the things it can do is self-generate. It can self-generate many cells, each of which I can change the name of the cell: S1, S2, S3, S4. This is equivalent to mitosis. Mitosis is just divided into two cells. They say it's identical. They are not identical. They are in different positions. Okay, so they're not identical. Same thing with my S1, S2. They are identical, but their names are different. Okay, so this is theory, practice versus theory. Reality to practice. Theory is virtual reality. Okay, so pole science, we demonstrate all our theories. We demonstrate our value theory by predicting for the Federal Reserve chairman that the subprime loan savings loan crisis. Now I have students who are coming to extend the research on this mitosis. Mitosis we already demonstrate, but meiosis is very, very different. Okay, it's very, very difficult. It's combination of cell into a stem cell, and it will multiply, and they eventually become human. Okay, that will be interesting. Okay, things become interesting. In mitosis, there's not much; just divide the cell. You see, in meiosis, everything happens there. Okay, including human cloning. So I have students working on it, and I hope they can produce some result. I'm too busy, too busy dancing, and this hour, right here in California, 7:00. It's a bad time for me because it's not too early, not too late. right in the middle where I get really tired, I have to rest. Then I start to get up. So basically, my schedule is such that dancing is from 11:00 to maybe 3-4 o'clock. Then thinking is after 10:00. So basically, if Sheriff wake me up, then I will go because he's supposed to be my student, supposed to do double hitting. But if he doesn't send me a video on double hitting, I will not wake up.
Okay, thank you, Professor Ching. Professor Donald, yes. Can you unmute, please?
Well, what a lot of people were talking about, a couple of people talked about the idea of three-dimensional, or pointed out the idea of three-dimensional for geography. David was talking about mapping, and we're used to that. Think of Google Earth. We can look at the dimension, the elevation of things from Google Earth. And from Google Earth, we can walk down the street and we can look at look at the doors of houses and walk. When I remember I was in Finland and trying to find my way around, and I could use Google Earth, and it would show me the door of the place that I was trying to find when I got there, so I could find exactly where I was going. And that's a three-dimensional map, the same kind of three-dimensional map that I was talking about that cars use. Just think of the amount of data that those things are pushing back and forth. That's one of the reasons I said I don't think it's going to work very soon in rural areas. And I think it's going to work better and better as we go to 5G, because the amount of data that's getting pushed back and forth. The synergy that was being I think was talking about between the artificial intelligence and the graphics, it has a lot to do, for one thing, that the GPUs were originally invented for graphics. You know, they're incredible array processors. You can describe 3 dimensions in 2 dimensions. You've seen those maps where they basically are maps of the globe that are they're done like this, where they're like slices. The globe is laid out in pieces like that, or the globe is stretched out. So Antarctica is huge, and Australia looks as big as, and Greenland looks as big as South America. Those are projections, but all of the globe is there. And if you know mathematically how to switch back and forth, you can put 3 dimensions into 2 dimensions. So you could just use array processors to do three-dimensional. So the one thing that I keep saying is that when we'll talk about I'm glad we're going to be talking more about artificial intelligence next time, but artificial intelligence, it can't make guesses. So like while I was here, I want to clean up my office, and I was thinking, gosh, I've got these little things that I put eye drops in. And I'm thinking, I wonder what I should do with those. They're scattered all over my office. And I looked around, and I have a box that's for index cards. And it's got a lid on it. And I thought to myself, oh, well, I don't want to put them in there, because if the lid is on them, then I won't notice where they are. And then I said, oh, what I could do is I could just put the lid on the bottom so it's open. So what I just did is I formed a hypothesis. It may not work. I can do it, and I'll do that, and I'll run this little experiment. Well, computers can't do that at all. And that's something that we're constantly doing in our lives. And in order to be able to exist in the world, we have to be able to do that. My cat does that. One-celled organisms do that. Ants do that. But computers can't do that, and we have no idea how to get them to do that. So they're not going to. It's going to be a while before we get them to do that. And the idea that we don't really see in 3 dimensions, I think, is like kind of an example of how computer scientists don't get what humans do. So computer scientists have a tendency to make guesses about what humans do without really understanding, because we do see in 3 dimensions in a sense, because we really don't act on the world around us. We act on a model that we build of the world around us in our brain. And so that model is in 3 dimensions, the model that we build in our brain. And that model is built in the same way I'm talking about, built by guesses. So we have a 3-dimensional model of the world in our brain that's based on our guesses of what's around us, and partially because we've seen what's in back of whatever. We've walked around the room before, so we know what's in the room, and then partially our guesses about what is in rooms normally or generally. And that's why it's really difficult to do a self-driving car by simply artificial intelligence and three-dimensional imaging. I thought that was so clever. That's a beautiful way to solve the problem, because artificial intelligence won't do it. But using a Waze system to be able to completely constantly be mapping the city and remapping it, that's a beautiful solution, and I'm excited by that, because I've always wished there were self-driving cars, and I was bummed out that it was going to take so long. But this is actually working, and it's going to be something that we're going to be able to start using relatively soon. So I think three-dimensional imaging is something that's an exciting part of our lives now.
Thank you, Professor Donalds. I have to go for the concluding remarks for today's session. Our fellow from World Talent Economy Forum, Mr. Adam, what you want to add as a concluding remarks for today's session?
Thank you, Sharif. I was thinking about your question to Professor Francis about the youth community, and I think the youth have engaged with some of what we're talking about. Deepfakes for entertainment and humor have already become quite popular on YouTube in particular. There's a very creative and funny and experimental artistic and creative subculture where content creators are having fun deepfaking Sylvester Stallone's face onto a ballerina, for example. It's a gold mine of content creation and memes as well, of course. The deepfakes are very memeable and memorable. I feel like sometimes I'm the techno-pessimist of these discussions. I might have to try and change tack and balance out into a more techno-optimist angle a bit. But similar to what I touched upon before, I think higher and higher video resolution will be applied to surveillance, of course, and algorithms and AIs could eventually be clever enough to fill in the blanks and empty spaces, to color in blind spots. Say, for example, I'm walking down the road, I show up on the monitor, and then it follows me, and then I walk behind a wall. Of course, on the monitor is just the wall, but the brain of the system will be able to calculate and render where I am behind the wall still, how fast I am walking, and what direction, using my previous trajectory and the movements of air molecules and trees that I'm having an impact on, microscopic impact on, as I'm walking behind the wall. So the impact that would have on surveillance would be massive, and other fields such as archaeology as well, a bit less dramatically. In fact, early generations of this kind of speculative simulatory imaging and visualization has already been put to use in archaeology, where you can scan a broken plate or a piece or a broken shard from a clay pot or a plate, and then use software to reconstruct within cyberspace what the object originally looked like at the time it was being used, back in ancient times or whenever, with all different colors and paints as well as the shape, obviously. So through enough generations and iterations and improvements and such technologies, we might be able to resurrect the Library of Alexandria and the Colossus of Rhodes, or the Hanging Gardens of Babylon near perfectly, and then 3D print all the historical wonders of the world again. We might need to make space, though, or migrate the wonders of the Earth to Mars, where they will become the 7 wonders of Mars. And certainly one area I would like to see perfected within my lifetime would be the recording of dreams at night, and then being able to play them back and watch them the very next morning, say. That could have profound spiritual implications as well. Great topic. Thank you, Sharif.
Thank you. Mr. Marshall, what's your concluding remarks for today's session?
Well, I think it's been a terrific discussion today, Sharif. One thing that I noticed wasn't really articulated too much, although both Adam and Hugh did touch upon it. The actual, and Adam was just talking about 3D reconstruction in a way, like shards of pottery and things like that. This technology has been used for human health, as well as the negative issues that Adam brought up and Hugh has brought up as issues. It's used in medicine, and there's 2 methods. There's a passive method and an active method for 3D reconstruction. The 3D passive method is really a reconstruction that does not interfere with the object itself. whereas an active method kind of manipulates the image, as Adam has pointed out, that can create these different images. He calls them fake images. In medicine, obviously, what they're used for is they're used in scopes and they're used in operations and robotic operation technology. So there's a lot of opportunity here for growth in terms of human health and also for human good, just as well as there's always, like any other technology, it can be used for a negative purpose. I think that the idea of computer graphics and computer animation and computer vision and medical imaging and computational science are all combining together today to give us a panoply or a range of opportunities. And I would like to tie that, Sharif, into my concluding remarks with regard to the fact that there's an opportunity here for the developing world to participate in this and to get young people to sign up and take courses in these areas for the good of humanity, not necessarily for the bad. And so what we want to do is we want to encourage people to engage with people like our new guest on this panel, Dr. Cho and his team, to be able to bring forth these technologies to the developing world. And on that, I'm concluding my remarks.
Thank you, Professor David Smith. What's your concluding remarks for today's session?
I concur with what Marshall just said, and with what's there is that this is a great opportunity. I can see a lot of work still to be done in academia of all types. I can see work being done in particularly advancing the standards across, which will move us even further forward. And the entrepreneurship community, the emphasis of 3D, and particularly the ability as we begin to look at digital twins, and both human digital twins and manufacturing and others, they will only be enhanced by the application of higher resolution, higher fidelity, 3 dimensions, and the ability to model and simulate in 3D will continue to allow us to become more precise, more thorough in what we're trying to do, and hopefully we'll reduce errors and challenges as we go forward. But it's an exciting time to be able to apply this technology to more possible commercial areas than I can even imagine. So it's a great time for invention in this area around the world. So Sharif, thank you.
Thank you, Professor. Professor Cho, what's your concluding remarks for today's session? Can you unmute, please?
Oh, sorry. First of all, I really appreciate inviting me. It was a really great discussion, and I really enjoyed listening to the very different opinions and different experiences. And just like David said, I think the 3D technology, for me, 3D technology is kind of a very good tool for the young student to learn about the entrepreneurships, because it's easy to adopt this technology to start up their businesses as well. And also, this 3D technology is a very exciting tool to motivate students to learn the programming and the graphics and AI. It's a really great tool to learn about the new technology as well. And Adam mentioned several things about the different features of the 3D imaging, such as color, texturing, and the shape. Those are the depending on the applications and depending on the needs, some of the features need to be mixed together. Sometimes we can remove it or minimize it to represent the 3D with the optimal data sets. So I think I love to discuss lots of the new opportunities to integrate 3D instead of the in-depth research. I think lots of theoretical things has been already done, and there are lots of open areas we can adopt it. So I'm very interested in that area.
Thank you, Professor Cho. Professor Ching, what's your concluding remarks for today's session?
Oh yeah. First, welcome Francis to our discussion. I hope you come more often, because
Yes.
you know I'm sort of lazy.
Appreciate it.
Okay. In any case, as humans who have inherited the Earth, we should be working on most advanced topics. But today, in this knowledge, in this money-oriented society, we only work on short-term and monetary returns, while knowledge is by far has the highest rate of return, both long-term and short-term, and non-monetary as well as monetary. So that is, you know, to start. But I need to add something, which in my previous discussions is that the self-generating neural network of unlimited software cell correspond to mitosis. Mitosis is just cell division. And it also include applied to epigenetics and reprogramming of DNA. But those things altogether, they don't need graphics. Okay, only when you get to meiosis, the whole intelligence of the living system combined into one. Okay, you have hardware, software, and graphics all come together and also come out in terms of 3D printing. So this is very interesting, very, very challenging. So I have students working on this, and anybody who's interested in looking at this, it's very interesting thing to think about. Okay, you see how nature does it. You can start to see real the complexity involved. You see, you are not working with something. You just go in and work. You get a generator, software generator, which generate a program, which does things. Okay, just like in DNA protein system, you have DNA which does nothing. Then you generate protein, then protein does things. Okay, so this thinking is getting to be very interesting. I'm glad that you tried to get me to talk about this 3D graphics. It sort of expanded the range, and it will be encouraged to my students who I brought into to look at this thing. Very difficult to think. Another way, let me give you a very quick summary. You see, you self-generate, you generate self-generating a generator, and you have a common file. How do you design the common file will decide what will be the next generation of the self-generated cell looks like. Okay, thinking about this external common file is a very, very difficult problem. Okay, people need to be very good thinkers to think that everything is sort of indirect, and outcome can be just infinitely variable, infinitely complex. Okay, complete automation is the solution to unlimited complexity. So, so I would propose this problem of thinking the external common file as the most difficult thinking problem today.
Thank you. Thank you, sir. Professor Donald, what's your concluding remarks for today's session?
One thing we didn't mention is the incredible use of 3D graphics in movies. I mean, they've gotten to the point where they can make basically animation that almost looks like people now. I mean, they've gotten so good at it, and it fits towards what Adam said about the deep fakes. But and that's an incredible skill. And that has a lot to do with how our brain perceives what we see. Once I evaluated a startup that had you listen to speakers. They were just normal speakers, the kind that you have a strip underneath your television. And the guy was an expert at psychoacoustics from Bell Laboratories. He'd worked at Bell Laboratories forever. and he understood how your ear, how the sounds hit your ear that made you believe that the sounds were coming from behind you or next to you or wherever, and you could just listen to it, and you would hear the sounds in back of you or next to you or all around you. So it was complete surround sound without having surround sound. You could just, and it's an interesting thing. I mean, you've seen holograms where from a flat surface you see three dimensions. So what is going on in our brains that make us be able to see three-dimensional images? How does that work? So besides the wonderful, interesting technology of being able to create the graphical images on hardware and be able to analyze them with the inductive systems, deep learning and things like that, it's also incredibly interesting to start studying the neuroscience and the psychology of what's going on. I mean, how are humans perceiving this? And that's a critical part of all of this. And I think that if anybody's listening to this personally and thinking about a career path, if you learn enough neuroscience to start understanding what we know about this and being able to keep up with it and understand the literature as it evolves, and you learn enough computer science to be able to start implementing some of these kinds of things, you could probably charge $500,000 a year for your time. So that's how I'm going to conclude.
Thank you everyone for joining today's sessions. By today's discussions, we finish 552 episode. I want to give thanks to all of our speakers, those who regularly support World Talent Economy Forum. Especially, I want to give thanks to our audience. Please share our content as much as possible with your government, with corporations and academy. We try to minimize the gap in between developed world and developing world, definitely through the modern science, engineering, and technology. So if you have anything, I'm sure our honorable speaker, they're happy to support our audience. So thank you everyone, especially Professor David Smith, Professor Cho. This is first day for you, Mr. David, Mr. Adam, Professor Ting, Professor Donald, and Mr. Marshall. I want to give special thanks for your continuous support for World Talent Economy Forum. Thank you. Bye-bye and take care.
Nice meeting you all.
Thank
Bye.
you, everyone.
Good meeting you. Take care.
Thank you.